On the morning of September 27, 2023, a seismograph at the monitoring station on the western edge of the Campi Flegrei caldera in southern Italy registered a magnitude 4.2 earthquake. It was not the strongest earthquake to originate from this location in recent years. It was not the deepest. By the technical standards of seismology, a magnitude 4.2 is a moderate event, strong enough to feel, strong enough to startle the people of Pozzuoli, Bagnoli, and the western neighborhoods of Naples who felt their floors move and heard their walls creak, but not strong enough to cause structural collapse in well-maintained buildings. But this particular earthquake triggered something that the Italian National Institute of Geophysics and Volcanology, the INGV, had not activated for the Campi Flegrei system in years. They raised the alert level from yellow to orange. In the Italian civil protection system, yellow means the volcano is showing signs of unrest. Orange means the unrest has escalated to a degree that requires heightened monitoring and readiness for evacuation. Red, the level above orange, means eruption is imminent or in progress. The Campi Flegrei alert level had not been raised to orange since 1984. In 1984, 40,000 people were evacuated from the Pozzuoli area as the ground rose by more than a meter in a period of months, and earthquakes became a daily occurrence. The evacuation was ordered not because anyone believed an eruption was certainly coming, but because no one could rule it out. The evacuees never returned to their original homes. The crisis eventually subsided, the alert level was lowered, and life around the caldera resumed, incompletely, uncomfortably, with a persistent awareness among volcanologists and civil authorities that the system had not been resolved, it had only been paused. The 2023 Orange Alert did not produce a mass evacuation. The 2023 Orange Alert produced something more subtle, and in many ways more significant. It produced a formal acknowledgement by the scientific institution responsible for monitoring the Campi Flegrei system that the volcano was in a state of elevated and escalating unrest that exceeded the threshold of the yellow alert category. That acknowledgement was not made lightly. The INGV scientists who voted to raise the alert level understood what it meant. They understood the economic disruption it would cause. They understood the political sensitivity of declaring elevated volcanic risk in one of the most densely populated and economically significant areas of Europe. They raised it anyway because the data required it. We are going to explain what that data showed. We are going to explain what the ground beneath Naples has been doing in detail with the specific measurements and the specific physical mechanisms that explain why the world's leading volcanologists are watching this system with a level of attention that has no precedent in the modern era. But first, I need to give you the number that changes the scale of everything that follows. 3 million. 3 million people live within the hazard zone of the Campi Flegrei volcanic system, not within a radius of a hypothetical eruption vent. Within the caldera itself, within the geological structure that this volcano built over the last 39,000 years, within the boundaries of the system's last two massive eruptions, within the area where the ground moves, where the temperature of the shallow crust is elevated above normal, where the hydrothermal gases bubble up through the sea floor and seep from fumaroles on the hillsides. 3 million people are living inside a volcano. Most of them know it, none of them know what is coming, and this is not a metaphor. It is not a rhetorical exaggeration designed to provoke attention. It is a geological description of a demographic reality that has no parallel in the modern volcanic risk landscape. Every city near a major volcano is described as being near it, near Vesuvius, near Rainier, near Etna. The preposition establishes a spatial relationship. The city is in one place, the volcano is in another, and the risk is defined by proximity. Campi Flegrei is different because the city is not near the volcano. The city is inside it. The volcanic structure, the caldera, the hydrothermal system, the magma body at depth, extends beneath and around the metropolitan area of Naples, in a configuration where there is no clear boundary between the urban fabric and the volcanic system. The streets of Pozzuoli run across the caldera floor. The Bay of Pozzuoli fills the caldera's marine sector. The western neighborhoods of Naples sit on the caldera rim. The volcanic risk is not directional. It does not come from a specific bearing toward a mountain that is visible on the horizon. It comes from below, from the ground on which the city is built. This is the most important fact about Campi Flegrei, that most people who know its name do not fully internalize. 3 million people are living inside a volcano. Most of them know it. None of them know what is coming. And here is the specific fact that separates Campi Flegrei from every other volcano on this list. This is not a volcano with a mountain. There is no cone. There is no visible summit. There is no obvious visual metaphor for the threat. The caldera is a depression, a vast, shallow bowl in the landscape formed when the magma chamber emptied during the supereruption of 39,000 years ago, and the surface collapsed inward. Naples is built on the eastern edge of this collapsed structure. The port of Naples sits on it. The Bay of Pozzuoli, where tourist boats take visitors to see the submerged Roman ruins of the ancient harbour, is flooded caldera floor. The Roman temples at Pozzuoli, whose columns show the unmistakable marks of marine boring organisms at heights of 6 meters above the current sea level, are geological monuments to the fact that this ground has been rising and falling for 2,000 years, driven by the magmatic and hydrothermal system below. This is the most dangerous volcanic system in Europe, not because it erupts most frequently, not because it is the most powerful in terms of maximum possible energy release, but because it sits beneath 3 million people who have no mountain to warn them, no cone to watch, no lava flow to outrun. The threat from Campi Flegrei is not a river of lava. It is the ground itself, rising, cracking, heating, and then, if the system reaches a critical threshold, the explosion. The last time this system produced a major eruption was in 1538. That eruption built an entire new hill, Monte Nuovo, in a matter of days, and killed dozens of people who had not evacuated. It was not the largest eruption in the system's history. Not even close. It was what volcanologists call a small to moderate flank eruption, a relatively modest expression of a system that, in its most violent moments, has reshaped the entire Mediterranean. We are going to come back to 1538, but before we do, I need to tell you what the INGV's GPS monitoring network has been recording beneath Naples for the last 3 years, because the number that comes next is not a geological abstraction, it is a measurement. A specific, precise, continuously updated measurement of the ground surface above the Campi Flegrei caldera, and it is the highest value ever recorded in the modern monitoring era. To understand why Campi Flegrei is different from every other major volcanic system on Earth, you need to understand what a caldera is and what it means that 3 million people are living inside one. Most people's mental model of a volcano is a cone-shaped mountain with a crater at the top. When the cone-shaped mountain erupts, lava flows down the slopes, ash billows from the summit, and the danger is concentrated along the mountain's flanks. This model is accurate for a specific category of volcanoes, the stratovolcanoes, like Mount Vesuvius or Mount Rainier or Mount Pinatubo, and it is the model that most news coverage and educational material about volcanoes implicitly relies on. Campi Flegrei is not a stratovolcano. Campi Flegrei is a caldera system, and a caldera is not a volcano that erupted. It is the aftermath of a volcanic system that erupted so massively, so completely, that the magma chamber beneath it emptied faster than the overlying rock could be supported, and the surface collapsed inward. The collapse created a circular depression, the caldera, that can be tens of kilometers across and hundreds of meters deep. The Campi Flegrei caldera is approximately 12 to 15 kilometers in diameter. It stretches from the western neighborhoods of Naples across the entire Phlegrean fields, which is the literal translation of Campi Flegrei, the burning fields, to the coast of the Bay of Pozzuoli, and extends offshore into the bay itself. The caldera rim is not a dramatic cliff. It is a subtle landscape feature, a gentle rise in the terrain that most people who live within the caldera boundaries would not recognize as such without being told. Inside this caldera, the ground is active in ways that the landscape does not obviously reveal. Fumaroles, volcanic gas vents, emerge from the hillsides and from the seafloor in the Bay of Pozzuoli. The gases they emit are predominantly water vapor and carbon dioxide, with variable amounts of hydrogen sulfide that give the fumarole fields their distinctive sulfur odor. The Solfatara volcano, which sits within the caldera and was a popular tourist attraction for centuries, has fumaroles that vent steam at temperatures exceeding 160 degrees Celsius. The ground around the active vents is hot to the touch. The hydrothermal system, the network of heated water and gas that circulates through the fractured rock of the caldera, is the most direct expression of the magmatic activity below. The magma body beneath Campi Flegrei heats the rock and the groundwater above it. The heated fluids rise through the fracture network, emerging at the surface as fumaroles and hot springs. The circulation of these fluids is what drives the bradyseism, the slow rise and fall of the caldera floor, that has been observed at Campi Flegrei for at least 2,000 years. Bradyseism is the word that Italian volcanologists use to describe this phenomenon, derived from the Greek words for slow and earthquake. The caldera floor at Campi Flegrei rises and falls over decades and centuries in a pattern that reflects the changing pressure and temperature of the hydrothermal and magmatic system below. The Roman harbour at Pozzuoli, the ancient port city that sits at the centre of the caldera, shows the history of this bradyseism in its archaeology. The columns of the Temple of Serapis, a Roman market building that stands at the waterfront of modern Pozzuoli, are marked by the borings of marine mollusks at heights between 3 and 6 meters above the current sea level. These borings could only have been made when the columns were underwater. The columns were not always at the water's edge. The ground they stand on was once meters below sea level, submerged as the caldera subsided, and then rose again to its current elevation. The temple was built at or near sea level in the 1st century AD. By medieval times, the ground had subsided sufficiently that the market building was underwater. By the 16th century, the ground had risen again. The columns still stand, still marked by the evidence of their long submergence, a 2,000-year record of the caldera floor's restless movement. The 1538 eruption, the most recent eruptive event in the Campi Flegrei system, was preceded by a period of rapid bradyseismic uplift. Over the century preceding the eruption, the ground around Pozzuoli had been rising steadily. By the late 1530s, the uplift had accelerated. The inhabitants of the area observed the sea retreating from the shoreline, exposing former seafloor, and felt increasing earthquake activity. In the days immediately before the eruption, the earthquakes became nearly continuous. The population evacuated. On September 29, 1538, a new eruptive vent opened on the northwestern edge of the caldera, near the village of Tripagoli. Over the following days, the eruption built a new hill, approximately 130 meters high and 1,500 meters wide, Monte Nuovo, the new mountain. The eruption was violent but brief, lasting approximately a week. It killed at least 24 people who had returned to their homes too quickly after the initial explosions. Monte Nuovo still stands today, a low hill in the landscape of the Phlegrean fields. Visitors can walk to its rim and look into its crater. It is the youngest land in the Neapolitan area, built in a geological instant from the material ejected by the eruption. But Monte Nuovo is not the eruption that defines Campi Flegrei's hazard potential. The eruption that defines the hazard potential is the one that occurred approximately 39,000 years ago. The Campanian ignimbrite eruption, the supereruption that formed the Campi Flegrei caldera, was one of the largest volcanic eruptions in the last 200,000 years in Europe. It erupted approximately 300 cubic kilometers of magma in a massive ignimbrite, a pyroclastic flow deposit that covered a vast area of southern Italy and sent ash across the Mediterranean, the Middle East, and as far as the Caucasus and the Russian steppe. The Campanian ignimbrite eruption is the event that makes Campi Flegrei's caldera the shape and size it is today. It is the eruption that geologists use as the reference for what this system is ultimately capable of. The Campanian ignimbrite is not just an Italian geological event. Its consequences extended across the entire northern hemisphere. The volcanic winter produced by 300 cubic kilometers of material injected into the stratosphere caused a measurable reduction in global temperatures that persisted for years. The ash fall across Europe was thick enough to be preserved in sediment records from the Caucasus to Iceland. Some researchers have proposed a direct connection between the Campanian ignimbrite eruption and the final decline of the Neanderthal populations of Europe. The eruption at 39,000 years ago corresponds to a period of significant environmental disruption in European ecosystems and the sudden deterioration of habitat that would have followed a volcanic winter of this scale may have contributed to the pressures on Neanderthal populations that were already in competition with incoming anatomically modern humans. This connection is debated among archaeologists and paleoanthropologists. The evidence is circumstantial, the timing is suggestive, but the causal chain is difficult to establish definitively from the archaeological and geological record. What is not debated is the physical scale of the eruption or its climatic consequences. A caldera system capable of a 300 cubic kilometer eruption is not in the same geological category as a stratovolcano like Vesuvius or Pinatubo. Vesuvius's eruption in 79 AD, which buried Pompeii and Herculaneum and is perhaps the most famous volcanic event in Western history, produced approximately 4 cubic kilometers of material. The Campanian ignimbrite produced 75 times that volume. I am not telling you this to suggest that the Campi Flegrei system is about to produce another Campanian ignimbrite event. The monitoring data provides no support for that scenario. The magma volumes detectable in current geophysical surveys are consistent with a much smaller event if an eruption occurs. The current unrest is almost certainly telling us about processes at the scale of the 1538 eruption or a somewhat larger flank event, not about a caldera-forming supereruption. But the system's full geological history is the reason that the monitoring is as intensive as it is, the reason the alert system has 5 levels rather than 2, and the reason that the scientific community takes every escalation in the monitoring parameters so seriously. A caldera system that has produced a supereruption once can produce a supereruption again. The statistical probability in any given human lifetime is very small. The consequence if it occurred would be civilization scale. This is the specific combination of probability and consequence that makes Campi Flegrei unusual, not just among Italian volcanoes but among all volcanoes in the populated world. A repeat of the Campanian ignimbrite eruption is not what the current monitoring data is suggesting. The signal that the monitoring network is detecting is consistent with a much smaller event, comparable in scale to the 1538 eruption or smaller, or possibly no eruption at all. The current unrest does not require a supereruption to explain it. Hydrothermal processes, continued recharge of the magma system, and the ongoing response of the rock to the stresses imposed by decades of bradyseism are all capable of producing the signals currently being observed. But the history of the system is the reason that every measurement matters. Because this is a caldera system with a documented supereruptive past, no precautionary protocol can exclude the possibility of a larger event, and the 3 million people living within its boundaries are the reason that the 1538 scale event, a modest flank eruption by geological standards, is itself a catastrophe by any human measure. To understand what is happening right now, you need to understand the machine. Beneath the city of Naples and the Phlegrean fields, at depths ranging from a few kilometers to approximately 8 to 10 kilometers, there is a body of molten rock, not a uniform pool, not a simple chamber, a complex, heterogeneous zone of partial melt rock that is not fully liquid but contains a significant fraction of melt, interspersed with solid rock and saturated with dissolved gases that are waiting for the pressure reduction that will allow them to come out of solution. The magma body beneath Campi Flegrei is what drives everything visible at the surface. The bradyseism, the fumaroles, the seismic swarms, the ground deformation, all of these are expressions of the pressure, temperature, and fluid dynamics of the system below. The specific mechanism that makes Campi Flegrei so difficult to forecast is the interaction between the magmatic system and the overlying hydrothermal system. In a stratovolcano with a simple magma conduit, The path from the magma chamber to the surface is relatively direct. Pressure builds in the chamber, the magma rises through the conduit, and the eruption occurs at the summit or along the flanks. The monitoring signals that precede this sequence, harmonic tremor, surface deformation, elevated gas emissions, are well understood and in many cases provide warning times of hours to days. Campi Flegrei does not work this way. The magma body beneath Campi Flegrei communicates with the surface primarily through its influence on the hydrothermal system, not through direct magma ascent. The heat from the magma heats the water in the shallow rock. The heated water expands. The expansion pressurizes the rock. The pressurized rock lifts the surface. This is the bradyseism, not magma rising toward the surface, but hot water being pressurized by the magma's heat. This mechanism is important for understanding the monitoring challenge because it means that the standard volcanic precursors, the signals that indicate magma is rising toward the surface and an eruption is imminent, are not the primary signals at Campi Flegrei. The bradyseism signal, the seismic swarm signal, and the gas emission signal all reflect the state of the hydrothermal system more directly than they reflect the state of the magma body. This ambiguity is not a minor technical footnote, it is the central operational challenge of Campi Flegrei volcano risk management. When the INGB observes an increase in ground uplift, an increase in seismicity, and an increase in volcanic gas emissions at Campi Flegrei, they are observing signals that could indicate either a reactivation of the magmatic system that will eventually produce an eruption or a temporary perturbation of the hydrothermal system that will not. The data alone cannot currently distinguish between these two scenarios. This is not a failure of the monitoring system. The monitoring network at Campi Flegrei is one of the most comprehensive in the world. Dozens of GPS stations, seismographs, tiltmeters, gas analyzers, and underwater sensors covering the caldera continuously. The data quality is excellent. The issue is that the physics of the caldera system does not currently allow scientists to distinguish between the eruption precursor scenario and the non-eruptive unrest scenario using the available measurements. The uncertainty is fundamental, not instrumental. There is a third layer of complexity in the Campi Flegrei system that makes it even more difficult to interpret than the hydrothermal magmatic ambiguity alone. It involves the mechanical behavior of the rock above the magma body. The rock beneath Campi Flegrei has been subjected to hydrothermal alteration for thousands of years. The hot acidic fluids circulating through the system convert the primary rock minerals into secondary minerals, clays, zeolites, and other alteration products that have very different mechanical properties from the original rock. Hydrothermally altered rock is typically weaker and more permeable. It fails at lower stress levels, it fractures more readily. It can create pathways for the upward migration of magmatic gases and fluids at lower pressures than would be required to fracture fresh rock. This means that the threshold for eruptive activity at Campi Flegrei may be lower than standard models assume. The pressures required to open a new eruptive fracture to the surface may be achieved at lower magmatic pressure levels than a fresh volcanic system would require. The implications are significant. If the rock failure threshold is lower than the models assume, the transition from the current unrest state to a pre-eruptive state could occur at monitoring signal levels lower than the alert criteria detect as strongly concerning. Researchers are actively working to characterize this uncertainty through rock mechanics experiments on samples from the Campi Flegrei hydrothermal system and through modeling studies incorporating the altered rock properties. Now let me explain what has been happening in the data over the last 3 years, because the specific pattern of the current unrest is what makes it qualitatively different from previous episodes. Since approximately 2005, the Campi Flegrei system has been in a period of sustained uplift. The ground surface in the central uplift zone, in and around Pozzuoli, has been rising continuously, with intermittent accelerations for nearly 2 decades. The total accumulated uplift since 2005 is now approximately 1.3 meters, 1 meter and 30 centimeters in 20 years. For comparison, The crisis episode of 1982 to 1984, which produced the mass evacuation of Pozzuoli, accumulated approximately 1.8 meters of uplift over approximately 2 years. The current episode has been slower and more protracted than the 1982 to 1984 crisis, but its cumulative magnitude is now approaching the same order as that crisis, and the rate is not decreasing. The GPS network data for 2022, 2023, and 2024 shows an acceleration of the uplift rate. The annual uplift that the system was producing in the early phase of the current episode, a few centimeters per year, increased to 20 to 30 centimeters per year in 2023. The 2023 value is the highest annual uplift rate recorded at Campi Flegrei since the 1982 to 1984 crisis. Simultaneously, the seismicity rate, the number of earthquakes being produced by the system per unit time, increased dramatically in the same period. The earthquake swarm of September 2023, which triggered the alert level increase, was the most intense seismic episode at Campi Flegrei in decades. The months following the swarm continued to show elevated seismicity, with hundreds of small earthquakes per month, compared to the background rate of a few dozen. The gas emission data adds a third line of converging evidence. The composition and flux of volcanic gases from the fumarole fields and from the seafloor vents in the Bay of Pozzuoli have been changing. The ratio of magmatic gases, gases that are released from magma as it ascends or degasses, to hydrothermal gases has been increasing, suggesting that the magmatic contribution to the system is growing. The carbon dioxide flux from the caldera has been increasing. The temperature of the fumaroles has been increasing. 3 independent measurement systems, ground deformation, seismicity, and gas emissions, are all showing escalating trends simultaneously. In volcanology, when multiple independent monitoring parameters escalate simultaneously, it is called unrest. When the escalation is sustained over years rather than weeks, it is called deep-seated unrest. When the escalation crosses defined thresholds, the alert level is raised. The Campi Flegrei system is currently showing deep-seated unrest that has been escalating for 2 decades and has accelerated significantly in the last 3 years. This does not mean an eruption is certain or imminent. The scientific community is explicit about this uncertainty. The system could continue to show escalating unrest for years more before any eruptive activity. It could stabilize. The unrest could gradually decrease as the hydrothermal pressure is released through the crack systems without reaching the threshold for an eruption, or it could not. And that is the specific uncertainty that makes Campi Flegrei the most operationally challenging volcanic system in Europe. Here is the question that every volcanologist working on Campi Flegrei is asked at every public meeting, in every media interview, at every conference where the system's current state is discussed. Is it going to erupt? And here is the answer that the most honest and most knowledgeable scientists in the field give. We don't know. This is not evasion. This is not false modesty or institutional caution designed to avoid legal liability. It is an accurate description of the state of scientific knowledge about a system that is, by any measure, one of the most studied volcanic systems in the world. The reason that the answer is genuinely unknown comes down to 2 fundamental challenges that cannot be solved by more instruments or better data. The first challenge is that we do not know, from the monitoring data alone, whether the current unrest represents the precursory phase of an eruption or a prolonged non-eruptive restlessness that will eventually subside. The signals of the 2 scenarios overlap. Every eruption that has ever occurred at a volcanic caldera system has been preceded by some period of ground deformation, seismicity, and gas emission changes. But not every period of ground deformation, seismicity, and gas emission changes has been followed by an eruption. The historical record of caldera systems around the world contains numerous examples of intense and prolonged unrest episodes that did not end in eruptions. Episodes that lasted years or decades, produced dramatic monitoring signals, forced evacuations, and then subsided without a volcanic event. The Campi Flegrei crisis of 1982 to 1984 is one such example. The uplift, the earthquakes, the fumarolic activity, all were real, All were concerning, all justified the precautionary evacuation, and there was no eruption. A volcano scientist looking at the current data at Campi Flegrei has no tool available that definitively distinguishes between this is going to erupt and this is going to subside without erupting. The signals they are measuring are necessary conditions for an eruption, but not sufficient conditions. The second challenge is that even if an eruption were to begin, the warning time between the onset of pre-eruptive signals and the eruption itself could be extremely short for a caldera system of this type. For stratovolcanoes with clear magma ascent pathways, the sequence of events preceding an eruption, from initial deep seismicity indicating magma movement through intermediate depth seismicity as the magma approaches the surface, to shallow seismicity, surface deformation and gas release, typically takes hours to days. This gives emergency managers time to order evacuations and populations time to respond. For a caldera system like Campi Flegrei, where the primary monitoring signals reflect the hydrothermal system rather than magma ascent, the transition from the current state to an eruption could be much more rapid. If a new eruptive vent opens, as one did in 1538, the critical precursory signals directly attributable to the vent formation might appear hours before the eruption rather than days. The 1538 eruption's precursory period is not well documented by modern standards. The written records of the time describe several days of earthquake activity before the eruption. Whether those earthquakes provided sufficient warning time, and whether the population of a modern urban area with millions of residents and complex transportation infrastructure could respond effectively to a few days of warning, is a question that Italian civil authorities have been trying to answer for years. The answer is uncomfortable. The official evacuation plan for the red zone of Campi Flegrei, the zone of highest risk, closest to the most likely eruptive vents, covers approximately 500,000 people. The plan envisions evacuating this population in 72 hours. The transportation analysis underlying the plan is based on the road network capacity and the available rail and maritime transportation options. The plan has been criticized by researchers who argue that the 72-hour timeline is optimistic. Traffic modeling studies of a mass evacuation from the Naples metropolitan area, where traffic congestion under normal conditions is severe, where the road network passes through narrow urban streets and coastal corridors with limited capacity, where a simultaneous volcanic emergency would likely be accompanied by earthquakes damaging roads and bridges, suggests that evacuating 500,000 people in 72 hours would require a level of coordinated, compliance-complete response that has rarely, if ever, been achieved in real-world mass evacuation scenarios. And 500,000 is the red zone population. It is not the 3 million people who live within the broader caldera zone. The broader zone, the yellow zone, in Italian civil protection terminology, includes areas that would be affected by ashfall, by toxic gas emissions, by flooding from heavy rains mixing with volcanic ash to produce lahars, and by the indirect consequences of a major volcanic event in the center of a metropolitan area. These populations are not included in the 72-hour evacuation plan. They are expected to shelter in place or self-evacuate through the same road network that is simultaneously being used by the red zone evacuation. The Italian government and the Campania regional authorities have invested substantially in improving the evacuation plan, the public communication system, and the physical infrastructure of evacuation routes in recent years. Progress has been made. The challenge is not one of indifference. It is one of physics, the physics of moving 3 million people rapidly through a road and rail network that was not designed for simultaneous mass evacuation, in response to a volcanic system that may provide hours rather than days of final warning. This is the blind spot, not the volcano's unrest itself. The planning assumptions about what kind of warning is available and whether the population can act on it in time. Let me give that blind spot a specific human shape. The 2016 study of evacuation dynamics in the Naples metropolitan area, conducted by a team of researchers at the University of Naples Federico II, using agent-based traffic modeling, simulated the execution of the red zone evacuation under various warning time scenarios. The study found that under optimal conditions, full compliance with evacuation orders, no traffic accidents, no road damage from earthquakes, functioning signal systems, the red zone could be cleared of private vehicles in approximately 56 hours. The plan calls for 72 hours. Under optimal conditions, the model suggests 56 hours is achievable. But the study's optimal conditions scenario assumed none of the disruptions that a volcanic emergency actually produces. When the researchers added realistic assumptions, a 15% non-compliance rate for evacuation orders, a 10% reduction in road capacity from earthquake damage, a 20% increase in travel times from counterflow operations, the clearance time for the red zone extended to 84 hours, longer than the plan's target, under realistic but not extreme assumptions. When the researchers added the self-evacuation of yellow zone residents to the traffic model, the people who are not under mandatory evacuation orders, but who will leave anyway when they see smoke rising from the caldera and feel the earthquakes, the red zone clearance time extended further, because the voluntary yellow zone evacuees are using the same roads as the mandatory red zone evacuees. And when the researchers modeled the scenario where the warning time is not 72 hours but 36 hours, which is within the plausible range for a Campi Flegrei eruption based on the geological record, the red zone was not fully cleared before the eruption began in any of the simulated scenarios. These findings were published in a peer-reviewed journal. They were presented at civil protection conferences. They are known to the Italian emergency management community. The response has been to continue improving the plan, updating the traffic management protocols, investing in evacuation route infrastructure, conducting drills that test compliance and coordination. All of these improvements matter. But no improvement to the evacuation plan can solve the fundamental physics of moving 500,000 people through a fixed road network in a compressed time frame, while the ground is shaking and the volcano is preparing to erupt. This is the blind spot, not the volcano's unrest itself. The planning assumptions about what kind of warning is available and whether the population can act on it in time. Let me take you through the current monitoring data for Campi Flegrei in the same way that the INGV duty scientists look at it every morning. The GPS network is the foundation. There are more than 30 continuous GPS stations distributed across the caldera, providing real-time measurements of the ground surface position in 3 dimensions, horizontal movements and vertical uplift. The data updates continuously and is transmitted to the INGV's monitoring center in Naples. The primary reference point for the current unrest is the benchmark in the center of Pozzuoli, which has been the reference for caldera floor measurements since the 1970s. This point has accumulated approximately 1.3 meters of net uplift since 2005. The rate of uplift at this point in 2023 was approximately 22 centimeters in a single year. For context, 22 centimeters of ground uplift in a year is not something you would necessarily notice in daily life if you were not looking for it. The ground does not crack visibly. Buildings do not obviously tilt. The change is distributed over a broad area. The entire caldera floor rises more or less together, like a slowly inflating bubble, and the individual millimeters of daily uplift are imperceptible to the human body. But the cumulative effect of sustained uplift on buildings and infrastructure is significant. Campi Flegrei's uplift episodes have historically caused structural damage to the older buildings of Pozzuoli and the western Naples suburbs. The masonry construction that characterizes much of the older urban fabric in this area, multi-story apartment buildings from the 19th and early 20th centuries, is particularly vulnerable to the differential movements that accompany bradyseism. The buildings move with the ground in the vertical direction, but the horizontal gradients in the uplift pattern cause subtle differential displacements that crack facades, misalign door frames, and, in severe cases, compromise structural integrity. The structural vulnerability of the building stock in the Campi Flegrei risk zone is not a minor technical footnote. It is a humanitarian risk factor. If a major earthquake, larger than the magnitude 4.2 of September 2023, occurs during the current unrest episode, the structural damage to the older masonry buildings of Pozzuoli and western Naples could be severe. And seismically damaged buildings are a much larger problem in a volcanic emergency because they cannot serve as shelter and may need to be evacuated simultaneously with the volcanic precautionary evacuation. The seismic monitoring network at Campi Flegrei operates 24 hours a day and processes thousands of events per month at the current activity level. The September 2023 swarm produced the largest single earthquake, magnitude 4.2, observed at the caldera in years, and was accompanied by hundreds of smaller events over the following weeks. The seismic activity has remained elevated since the swarm, with background rates substantially above the pre-2020 levels. The seismicity is shallow. Most earthquakes in the current swarm cluster at depths of 0 to 4 kilometers within the upper part of the hydrothermal system, rather than at the depths associated with the magma body. This is both reassuring and ambiguous. It is reassuring because shallow seismicity is often associated with hydrothermal fluid movements rather than direct magma ascent. It is ambiguous because shallow seismicity is also what precedes the opening of new eruptive vents in caldera systems, the fracturing of shallow rock by the pressurized fluids that would eventually create the pathway for an eruption. The gas monitoring network measures the composition and flux of volcanic gases from the fumarole fields at Solfatara and Pozzuoli. The monitoring at Pozzuoli, a fumarole field on the eastern edge of the Solfatara complex that has become the most active in the current unrest episode, shows temperatures that have been increasing since 2019 and reached over 160 degrees Celsius by 2023. The carbon dioxide flux from the Pozzuoli fumaroles has been consistently elevated, and the ratios of magmatic to hydrothermal gas species have been shifting toward a more magmatic signature. The seafloor monitoring, a network of instruments deployed on the floor of the Bay of Pozzuoli, provides information about the submerged part of the caldera that is not accessible from land. The seafloor instruments show seafloor deformation consistent with the onshore GPS data, confirming that the bradyseism is occurring uniformly across the caldera, including its submerged western sector. They also detect seafloor gas emissions and temperature anomalies that confirm the continuation of the hydrothermal activity in the submarine part of the system. All four monitoring streams are telling the same story. The system is loaded. The pressure in the hydrothermal system is elevated. The seismicity is elevated. The gas emissions have a strengthening magmatic signature. The ground has risen 1.3 meters, and the uplift rate is at its highest value in decades. Is this the precursor to an eruption? The data cannot say yes. The data cannot say no. But there is a specific comparison that gives the data its sharpest context, and it is a comparison that the INGV's own publications make directly. The 1982 to 1984 crisis that produced the mass evacuation of 40,000 people began from a baseline of approximately 60 centimeters of cumulative uplift that had accumulated since the 1970 episode. The crisis itself added approximately 1.8 meters of additional uplift in approximately 24 months, with the maximum uplift rate occurring in late 1982 and early 1983. The current episode began in 2005 from a baseline of essentially zero net uplift above the 1984 post-crisis level. The current episode has accumulated 1.3 meters of uplift over approximately 20 years, a much slower rate than the 1982 to 1984 crisis, which is one of the reasons that the current episode has not yet triggered the same level of emergency response as the 1980s crisis. But here is the comparison that matters. The starting position of the caldera floor for the current episode is not the starting position of the 1982 crisis. It is 1.3 meters higher. The current caldera floor position before any additional uplift from the next phase of the current episode is already at approximately the elevation it would have reached if the 1982 to 1984 crisis had continued at its rate for a full 3 years instead of 2. In other words, the ground is already where a previous crisis took 2 years of elevated activity to reach, and it is continuing to rise. The specific question that ING researchers are examining in the context of this comparison is whether the mechanical state of the shallow crust, already having been through the deformation cycles of the 1970s episode, the 1982 to 1984 crisis, and the current 20-year uplift, is more or less resistant to fracture opening than it was before those previous episodes. The answer from rock mechanics and from the seismic data is complex. The shallow crust has been repeatedly fractured and sealed. The current seismic activity is opening new fractures along orientations that were not active in previous episodes. The fracture network through which volcanic gases and fluids rise to the surface is evolving in ways that the monitoring network can detect through changes in where and at what depth the earthquakes are occurring. The caldera is not the same geological object it was in 1982. It has been changed by the episodes it has been through, and that changed state, more fractured, more permeable in some places, hydrothermally altered in ways that reflect decades of elevated fluid flow, is what the current monitoring is observing. What the data can say, what the INGV concluded when it raised the alert level to orange, is that the system has crossed a threshold of concern that requires a higher level of operational readiness. The threshold is based on multiple parameters crossing defined limits simultaneously, not one indicator exceeding its threshold, which can happen in normal variability. Multiple indicators crossing their thresholds together in a coherent pattern that suggests the system is responding to a common driver. That driver is the magmatic system below. Between 2014 and 2019, the Campi Flegrei system showed a period of relative stabilization. The uplift rate slowed, the seismicity rate decreased from the elevated levels of the 2012 to 2013 period. The fumarole temperatures at Solfatara and Pisciarelli remained high but showed less dramatic increases. The system was still showing unrest. The ground was still above its 2005 starting position, still being held up by the pressurized fluids below, but the rate of change was slower. In the language of volcanic monitoring, this period is sometimes described as a plateau phase. The system had reached a new elevated baseline and was not obviously accelerating further. This was not the same as returning to normal. The ground was still anomalously high. The hydrothermal system was still showing elevated activity. But the trend of continuous escalation had paused. And in the gap between scientific attention and public attention, something happened that happens in every volcanic risk management situation, where the immediate threat signal softens. The political and social urgency around the evacuation planning issue decreased, not among the INGV scientists, not among the INGV's technical publications, which continued to document the ongoing unrest and to flag the cumulative deformation as a concern, but in the political and public discourse around what to do about the 3 million people living in the caldera. The softening of the monitoring signal corresponded to a softening of the urgency around the difficult and expensive work of evacuation planning. The incentive structures of democratic politics are not well suited to sustained investment in preparing for risks that are not currently producing headlines. An eruption at Campi Flegrei would be catastrophic. Preparing for it is expensive, disruptive, and politically costly. The benefits of preparation are realized only if the eruption occurs, and they are realized invisibly in lives saved and damage avoided, not in dramatic visible outcomes. The plateau phase of 2014 to 2019 provided the political space for the preparation investment to slow. Then, in 2020, the system began moving again. The uplift rate began increasing. The seismicity rate began increasing. By 2021, the monitoring parameters were clearly trending upward again. By 2022, the annual uplift was tracking toward values that had not been seen since the early phase of the crisis-era episodes of the 1970s and 1980s. By 2023, the uplift rate was 22 centimeters per year, and the September earthquake swarm pushed the INGV to raise the alert. The plateau phase had ended. The escalation had resumed. The 6 years of relative quiet had not been followed by a return to the long-term background state. They had been followed by a resumption of escalation from the elevated baseline that the plateau phase had maintained. The system had not been recovering during the quiet years. It had been recharging. The distinction between recovery and recharge is not semantics. It is the difference between a threat that is diminishing and a threat that is accumulating. Consider the analogy of a slowly filling reservoir behind a dam. During periods of low inflow, the quiet years, the water level may rise slowly or not at all. An observer watching only the surface of the reservoir might interpret the slowdown in water level rise as evidence that the inflow has stopped and the risk of overflow has decreased. But if the inflow has not stopped, if water is still entering the reservoir at a slow rate, still adding to the total volume, then the quiet years are not years of decreasing risk. They are years of slow, continued accumulation toward the same eventual threshold. The Campi Flegrei caldera system, during the plateau phase of 2014 to 2019, was not releasing its accumulated pressure. It was maintaining it while adding to it at a slower rate. The magmatic heat input from below continued. The hydrothermal fluid inventory in the shallow crust remained at the elevated level that the previous years of pressurization had created. The locked zones in the caldera's shallow structure, the fault segments and fracture zones whose failure produces the seismicity, continued to accumulate stress. The plateau phase gave the civil protection system and the political apparatus a period of reduced urgency. It did not give the volcanic system a period of reduced loading. When the system began to accelerate again in 2020, it did so from a starting point that was further along the pathway toward eruptive conditions than it had been in 2014. The recharge that occurred during the quiet years was real, invisible at the surface, and consequential for the system's subsequent trajectory. The distinction between recovery and recharge is not semantics. A recovering system is one where the underlying driver, the magmatic pressure, the hydrothermal fluid inventory is decreasing. A recharging system is one where the driver is being replenished from below while the surface expression temporarily stabilizes. The monitoring data from 2024, when examined alongside the data from the plateau phase, is more consistent with the recharge interpretation than with the recovery interpretation. The magmatic system below Campi Flegrei did not lose energy during the quiet years, it gained it. Let me give you the economic and human geography of the Campi Flegrei risk zone in terms that make the scale of the potential impact concrete. The Naples metropolitan area, the Città metropolitana di Napoli, has a population of approximately 3.1 million people. It is the third largest metropolitan area in Italy after Rome and Milan. It is the economic heart of the Campania region and the most economically significant urban area in southern Italy. It generates a gross domestic product of approximately 60 billion euros annually. The Port of Naples handles approximately 22 million tons of cargo annually, making it one of the most active commercial ports in the Mediterranean. It is also one of the principal cruise ship destinations in Europe, receiving several thousand cruise calls per year and millions of passengers annually. The railway infrastructure of the Campania region converges on Naples. The high-speed rail line connecting Naples to Rome and through Rome to Milan and northern Italy passes through the eastern edge of the caldera zone. The regional rail network, serving the Phlegrean fields and the areas west of Naples, the Cumana and Circumflegrea lines, runs entirely within the caldera. The NATO Joint Force Command in Naples, one of the key command nodes of the NATO alliance's southern flank operations, is headquartered at the Lago Patria military complex in the northern part of the Campi Flegrei zone. All of this, the population, the economic activity, the port, the rail infrastructure, the military command node, sits within the volcanic hazard zone. The specific scenarios that the Italian civil protection models for Campi Flegrei range from a small eruption comparable to 1538, which would primarily affect the red zone population closest to the red vent, to a larger eruption comparable to the 4000-year-old Agnano Montespina eruption, which would produce pyroclastic flows and substantial ashfall over a much larger area. The 1538 scale scenario is manageable with a well-executed evacuation of the red zone. The population in the immediate vicinity of the most likely eruptive vents, roughly 500,000 people in the highest risk zone, would need to be moved before the eruption begins. If the warning time is sufficient and the evacuation is executed effectively, the primary risk to life in this scenario comes from the eruption itself, not from infrastructure failure. The Agnano Monte Spina scale scenario is a different category of event. The Agnano Monte Spina eruption, approximately 4,000 years ago, produced pyroclastic flows, fast-moving currents of hot gas and volcanic fragments that covered an area extending well beyond the caldera boundaries. The deposits from this eruption are visible in the geological record of a broad area around the caldera. A repeat of this event would not be contained by the red zone evacuation plan. It would require the evacuation of the entire metropolitan area. The evacuation of 3 million people from the Naples metropolitan area in the time frame likely to be available before a major caldera eruption is a logistics problem that has no satisfactory solution under current circumstances. The road network cannot accommodate the simultaneous outward movement of 3 million people and the inward movement of emergency response resources. The rail network, even at maximum capacity, cannot move the population fast enough. And the timeline for the transition from the current orange alert to the beginning of an eruption, while uncertain, could in the worst case be measured in hours rather than days. This is not a failure of planning or of political will. It is the physical reality of having built one of Europe's largest cities inside a volcanic caldera. The economic ripple effects of a major eruption at Campi Flegrei would extend far beyond the Campania region. Italian agriculture, particularly the productive agricultural zones of the Campania plain, which include the San Marzano tomato growing areas, the buffalo mozzarella production zone, and the wine-producing regions of the Campanian hills, would be severely affected by ash deposition. The volcanic ash that an eruption comparable to Agnano Monte Spina would produce could damage crops across hundreds of square kilometers and contaminate water supplies. The disruption to the port of Naples would affect supply chains for goods moving between northern Africa, the Middle East, and European markets through the central Mediterranean. The port handles a significant fraction of the automotive parts and consumer goods that move through the Campania logistics hub. The cultural and heritage sites of the Naples region, including Pompeii, Herculaneum, the Campi Flegrei Archaeological Park, and the historic centre of Naples itself, a UNESCO World Heritage Site, are in the potential impact zone. The Pompeii Archaeological Site, which receives approximately 4 million visitors per year, sits at the base of Vesuvius, approximately 20 kilometers from the centre of the Campi Flegrei caldera, far enough from the most likely eruptive vents to be outside the pyroclastic flow hazard zone for most modelled eruption scenarios, but within the ashfall zone for larger events. The tourism industry of the entire southern Italian coast, the Amalfi Coast, Capri, Ischia, the Cilento coast, would be affected by the evacuation and the volcanic activity, regardless of the eruption's physical footprint. The combination of population displacement, economic disruption, infrastructure damage, and cultural heritage loss in a major Campi Flegrei eruption scenario would produce a regional crisis of a scale that Italy has not experienced in the modern era. There is an important distinction between Campi Flegrei and its more famous neighbour, Vesuvius, that is often missed in public discussion of volcanic risk in the Naples area. Vesuvius, the cone-shaped mountain visible from most of the city of Naples, is the volcano that most people associate with the region. The eruption of 79 AD, which buried Pompeii and Herculaneum under meters of volcanic material, is the reference event. Vesuvius is monitored intensively and has its own red zone and yellow zone evacuation plans covering approximately 700,000 and 3 million people respectively. But Vesuvius has not erupted since 1944, when a relatively minor effusive eruption destroyed several villages on its slopes. The mountain has been in a quiescent phase for over 80 years. It is showing no significant unrest. Campi Flegrei, by contrast, is in active and escalating unrest right now. The alert level is orange. The monitoring data is showing the highest annual uplift rate in decades. The popular perception in Naples and in international media coverage is that Vesuvius is the active, dangerous volcano and Campi Flegrei is the background concern. The monitoring data says the reverse is true right now. Campi Flegrei is the active, escalating system. Vesuvius is quiet. This perception gap is one of the specific communication challenges that the INGV faces. When media coverage of volcanic risk in Naples focuses on Vesuvius, it creates a public mental model that is pointed in the wrong direction. The risk management attention of residents, civil authorities, and the insurance industry should be focused on Campi Flegrei in 2026, not on Vesuvius. The insurance industry's treatment of Campi Flegrei volcanic risk is instructive. Property insurance in the Campi Flegrei zone has historically been available. The Italian insurance market has not excluded the area from coverage, but the pricing has not fully reflected the current monitoring state. As the unrest has escalated since 2020, several major Italian and European insurers have begun reviewing their exposure in the zone and adjusting their risk models. The reinsurance market, which provides the financial backstop for catastrophic events, has been more proactive in pricing the risk. A major Campi Flegrei eruption would be an insured loss event of a scale that would test the capacity of the Italian insurance market and would require significant reinsurance and potentially sovereign support for recovery financing. The estimates produced by risk modeling firms for a 1,538 scale eruption, affecting the red zone range from 30 to 60 billion euros in direct insured losses. For a larger event affecting the broader metropolitan area, the figures approach or exceed 100 billion euros. The combination of population displacement, economic disruption, infrastructure damage, and cultural heritage loss in a major Campi Flegrei eruption scenario would produce a regional crisis of a scale that Italy has not experienced in the modern era. It is a Tuesday morning in late September. The Emergency Operations Center of the Italian Civil Protection Authority in Rome received, at 4:15 a.m., an alert from the INGV's Campi Flegrei monitoring center that the seismicity rate had increased sharply in the last 3 hours. The monitoring center's duty scientist, reviewing the GPS data alongside the seismic data, noted that the continuous GPS stations in the Pozzuoli uplift center had recorded approximately 3 centimeters of vertical movement in the preceding 12 hours. 3 centimeters in 12 hours. The background rate for the previous month had been approximately 2 centimeters per week. The duty scientist marked the observation as requiring immediate escalation and activated the INGV's internal protocol for potential volcanic crisis. By 7 a.m., the INGV's Volcano Monitoring Center had convened an emergency scientific committee. The data review showed seismicity rate 10 times the background, GPS uplift accelerating, fumarole temperatures at Pisciarelli spiking, and a broadband seismometer near the caldera center, recording a low-frequency tremor signal consistent with fluid movement at shallow depth. The committee's assessment was frank and unambiguous in its uncertainty. The system was showing precursory signals. The signals were consistent with the opening of a new eruptive fracture zone within the next hours to days. They were also consistent with a major hydrothermal discharge event that would not produce a surface eruption. The monitoring data could not distinguish between these two scenarios. At 9:30 a.m., the Italian Civil Protection Commissioner activated the Red Zone Evacuation Order. The order covered 500,000 people across 13 municipalities in the highest risk zone around the caldera. What followed was not the orderly, traffic-modeled, logistically planned scenario that the evacuation plan described. It was what happens when 500,000 people simultaneously try to leave a densely populated urban zone through a road network that was already congested at 9:30 a.m. on a Tuesday morning. The contraflow operations that the plan called for, converting inbound highway lanes to outbound, were implemented on the Tangenziale di Napoli, the ring road that circles the city. Traffic moved slowly. The rail network carried tens of thousands of people per hour on the lines whose routes were away from the immediate risk zone. But the human behavior element of mass evacuation was not conforming to the plan's assumptions. People in the yellow zone, outside the official red zone evacuation order, were leaving anyway. Not because they had been ordered to. Because they could see the smoke increasing from the Fumero fields, because the earthquakes were occurring every few minutes now, because the news broadcasts from the 3 television helicopters circling the caldera were showing ground cracks opening near Pozzuoli's waterfront and steam venting from new locations along the beach. By midday, the road network in the greater Naples area was approaching gridlock. The contraflow lanes were overwhelmed by the combined outflow of red zone evacuees following the official order and yellow zone residents self-evacuating outside the plan's parameters. At 2:47 p.m., a new eruptive vent opened on the southeastern wall of the caldera in a neighborhood of Pozzuoli, approximately 800 meters from the nearest residential buildings. The eruption began as a phreatic event, steam and gas explosions as the rising magmatic heat contacted shallow groundwater. Phreatic eruptions are among the least predictable volcanic phenomena. They occur when the heat from magmatic activity is sufficient to flash groundwater to steam faster than the pressure can be relieved through normal hydrothermal circulation. The resulting steam explosion can be sudden and violent. The transition from no surface activity to an active phreatic vent can occur in minutes. The 2014 eruption at Volcano in Japan, which killed 63 people, making it Japan's deadliest volcanic event since 1926, was a phreatic eruption. There had been no eruption at since 1991. The monitoring signals before the 2014 event were subtle. The eruption occurred with essentially no warning to the hikers who were near the summit at the time. Campi Flegrei's hydrothermal system is far more active than was before its 2014 eruption. The comparison is not to suggest that a Campi Flegrei phreatic eruption would be as sudden and as unheralded as The INGV's monitoring network is specifically designed to detect the precursory signals for this kind of event, and the elevated baseline of the current unrest means that the monitoring is already in a heightened state of alert. But the comparison is a reminder that phreatic eruptions, the kind most likely to be the first eruptive expression of a Campi Flegrei escalation, are the hardest type of eruption to forecast with precision, because they are driven by the physics of groundwater and not directly by magma ascent. The eruptions begin as a phreatic event, steam and gas explosions as the rising magmatic heat contacted shallow groundwater. The explosions were violent, audible across the caldera, and produced a dense column of ash and steam that rose to approximately 8 kilometers altitude. Within 20 minutes of the vent opening, the eruption transitioned to a magmatic phase. Incandescent lava fragments, lapilli and small volcanic bombs began falling in a radius of approximately 1 to 2 kilometers from the vent. The ash column grew to 12 kilometers. The ash began falling on Pozzuoli and the western neighborhoods of Naples. The evacuation, which had been partially orderly when ordered at 9:30 a.m., became chaotic as the eruption began. People who had been moving slowly through traffic jams abandoned their vehicles on highways and roads, creating obstacles for emergency vehicles and reducing the effective evacuation flow to a fraction of the plan's modeled capacity. The nearest residential buildings to the new vent, approximately 800 meters away, were evacuated by emergency responders on foot and by bus within the first 2 hours of the eruption. The residents of these buildings were the most immediately at risk, and their evacuation, while stressful and hurried, was achieved before the most intense phase of the eruption began. Over the following 12 hours, the eruption maintained a moderate intensity comparable to the early phases of the 1538 event. The ashfall covered an area of approximately 200 square kilometers around the vent. Roofs in some areas close to the vent received sufficient ash loading to pose structural risks. The Civil Protection Authority began a secondary evacuation of the ashfall-affected areas. The total death toll from the initial 24 hours was 31 people, not from pyroclastic flows or lava, but from vehicle accidents during the chaotic evacuation, from structural damage caused by the intense shallow earthquakes that preceded the vent opening, and from ash inhalation among elderly residents with respiratory conditions who could not be evacuated quickly enough. 31 people, in a volcanic emergency that had been planned for decades, that had a monitoring system of world-class quality, that had an official evacuation plan, that had days of orange alert warning before the escalation to the eruption phase. 31 people. In the 1538 eruption, 24 people died. The difference between 1538 and the simulation is not attributable to a failure of science or a failure of planning. It is attributable to the fundamental challenge of evacuating a modern metropolitan area through infrastructure that was not designed for mass simultaneous evacuation, in a time frame determined not by the plan but by the volcano. The monitoring data for Campi Flegrei is publicly available in near real time through the INGV's online platforms, and understanding how to read it gives you a picture of the volcano's current state that is more complete than any single news report can provide. The primary resource is the INGV Osservatorio Vesuviano website, ov.ingv.it, which is the operational monitoring center responsible for Campi Flegrei and Vesuvius. The site provides weekly bulletins summarizing the most recent monitoring data in accessible language. The bulletins cover seismicity, ground deformation from the GPS network, geochemical measurements, including gas flux and fumarole temperatures, and a brief assessment of the overall state of the system. The weekly bulletin is the most important single document for understanding Campi Flegrei's current state. It synthesizes all the monitoring streams into a coherent narrative and flags any significant changes from the previous week's baseline. When the bulletin's language shifts from describing stable or slowly changing conditions to describing acceleration or threshold crossings, it is telling you something important that may not be reflected in mainstream media coverage. The GPS data itself is available in graphical form on the INGV website, showing the time series of uplift at the key reference stations. The Pozzuoli benchmark time series, plotted against the historical record, shows the current uplift in the context of all previous episodes: the 1969 to 1972 episode, the 1982 to 1984 crisis, the current 2005 present episode. Seeing the current data point on that historical plot gives you the context that the abstract millimeters per year number cannot provide by itself. The seismicity data is available through INGV's real-time earthquake catalog, which provides magnitude, location, and depth for all recorded earthquakes above the detection threshold. For Campi Flegrei, filtering the catalog by the geographic coordinates of the caldera gives you the daily and weekly seismicity rate that the monitoring bulletins summarize. An increasing rate of earthquakes per day, particularly at shallow depths and in the central uplift zone, is one of the key signals to watch. The fumarole monitoring data, specifically the temperature time series from the Pozzuoli fumarole field, is available in the INGV monitoring bulletins and in the published scientific papers that the Osservatorio Vesuviano team produces regularly. The Pozzuoli temperature, which has been increasing since 2019, is one of the most directly interpretable indicators of the system's thermal state. When this temperature increases rapidly over a short period, it suggests that the heat input from below is increasing. The Italian Civil Protection Authority, Protezione Civile del Napoli. It maintains the public communication platform for volcanic risk in the Campania region. The alert level is displayed prominently and updates whenever the INGV provides a new assessment. The difference between yellow and orange is immediately visible on this platform and is the single most important public-facing indicator of the system's assessed risk level. When monitoring Campi Flegrei, the specific sequence of signals that would indicate a transition from the current elevated unrest toward an acute pre-eruptive state involves three converging indicators. First, a dramatic acceleration in the GPS uplift rate from the current approximately 2 centimeters per week to values exceeding a centimeter per day. Second, an increase in shallow seismicity rate combined with the appearance of low-frequency or tremor-like seismic signals that indicate fluid movement at shallow depth. Third, a significant increase in sulfur dioxide flux from the fumarole fields, the gas that is most directly indicative of degassing from ascending magma rather than from the hydrothermal system alone. These three signals together, if they converge over a period of hours to days, are the pre-eruptive signature that the INGMV's operational protocols are designed to detect. The monitoring system is specifically calibrated to detect this combination. The question that the monitoring cannot answer, the fundamental uncertainty that has characterized the scientific community's assessment of Campi Flegrei for decades, is what happens between the first appearance of these signals and the moment of eruption. The window might be days, it might be hours. In the worst case, for a shallow phreatic eruption triggered by sudden hydrothermal overpressure, it could be less than an hour. This uncertainty is the reason that the Italian Civil Protection Authority maintains a graduated alert system and population preparedness programs rather than relying entirely on last-minute warning. The best defense against inadequate warning time is a population that is already prepared and that can execute the first stages of evacuation as soon as the signal appears, without waiting for the final confirmation that an eruption is imminent. There is something I want to address directly before we close this documentary, because it is the question that underlies everything we have covered and that is almost never asked clearly in the public discussion of Campi Flegrei. Should 3 million people be living inside a volcanic caldera? The honest answer is that the question, while worth asking, is not practically actionable in a time frame relevant to the current unrest. Naples has been inhabited continuously for at least 2,800 years. Its position on the bay, its agricultural land, its port, its role in the trade networks of the Mediterranean. All of these factors drew human settlement to the Campi Flegrei area long before the volcanic risk was scientifically understood. The city was not built as a geological error. It was built where it was built because it made human sense. The Romans knew about the volcanic activity. The fumaroles at Solfatara were a tourist attraction in antiquity. Roman travelers wrote about them. The Cumaean Sibyl, the prophetic figure of Roman mythology associated with the volcanic landscape west of Naples, may reflect a cultural encoding of the experience of living beside an active volcanic system, where steam vents from the ground and the earth moves beneath your feet. The ancient city of Puteoli, modern Pozzuoli, was one of the most important commercial ports in the Roman Mediterranean world. It was where the Apostle Paul landed when he arrived in Italy, according to the Acts of the Apostles. It was the main port of entry for grain from Egypt, feeding the city of Rome. The Romans built their most important port city at the center of an active volcanic caldera, and they did so knowingly. The archaeological record of Puteoli shows multiple episodes of building damage, abandonment, and rebuilding that correspond to Brady seismic episodes. The city did not retreat from the caldera when the ground moved. It adapted. Buildings were repaired. New buildings were constructed with the experience of previous episodes incorporated into their design. The Roman engineers who built the Temple of Serapis, whose columns still record the history of the caldera's movements, were not ignorant of what they were building on. They built anyway because the location was too valuable to abandon. There is a word in Italian, campanilismo, that describes the intense attachment of Italians to their local community, their particular city or neighborhood, their specific place. For the people of Pozzuoli and the Flegrean fields, campanilismo is not just cultural sentiment. It is the accumulated relationship with a landscape that has been home to their families for generations, that contains their history, their language, their food, their monuments, and yes, their volcano. The 1983 evacuation of Pozzuoli produced a social trauma that is still present in the community's memory. Families that had lived in the historic center of Pozzuoli for generations were relocated to new housing developments on the eastern outskirts of the metropolitan area. Many of them never fully rebuilt the community networks that the evacuation severed. The old neighborhoods of Pozzuoli were partially repopulated when the alert level was lowered, but not fully. The social fabric had been torn in ways that 30 years could not entirely repair. This history is part of the context in which the 2023 Orange Alert was received by the population. The memory of 1983 and of the social disruption that followed shapes how the people of the Phlegrean fields respond to current warnings. Not with indifference, with a complex mixture of awareness and resistance, of knowledge and attachment, of fear and refusal to let fear determine the terms of their relationship with the place they were born. The Romans knew about the volcanic activity. The fumaroles at Solfatara were a tourist attraction in antiquity. Roman travelers wrote about them. The bradyseismic uplift and subsidence was observed and recorded. The volcanic nature of the landscape was part of the identity of the place. And the Romans continued to build and live there anyway, because the risk was manageable in the context of the resources and benefits the location provided. The modern metropolitan area of Naples is not so different in this fundamental calculation. The people of Naples and the Phlegrean fields live with an awareness of the volcanic risk that is deeper and more culturally embedded than the awareness of geological risk in most other places on Earth. The evacuation plans, the monitoring systems, the civil protection infrastructure, these are not alien impositions on a population that does not recognize the risk. They are the institutional expression of a community that has lived beside the volcano for millennia and has developed frameworks for managing the relationship. What has changed is the scale. The 2 million people of Roman-era Campania were not 3 million people with modern urban infrastructure and a national economy dependent on the port and the logistics network. The volcanic risk of 1538, which killed 24 people and built a new hill that is now a tourist attraction, is not the same risk as the volcanic risk of 2026, which would require the coordinated evacuation of a modern metropolitan area through infrastructure that was not designed for the purpose. The practical response to Campi Flegrei's unrest is not relocation, it is preparation, and preparation of a specific calibrated, honest kind. Preparation means knowing the evacuation plan. Every resident of the red zone should know their evacuation route, their assembly point, their destination, and how they would execute the evacuation with the specific constraints of their household, elderly family members, mobility limitations, animals, medications. The Italian Civil Protection Authority provides this information and conducts regular drills. Participation in those drills is not bureaucratic compliance. It is the difference between an orderly evacuation and a chaotic one. Preparation means understanding the alert level and knowing what it means for your specific situation. Orange does not mean evacuate now. It means the system is in an elevated state of unrest that warrants heightened readiness. When the alert level changes, it is a signal to review your preparations, confirm your route, and ensure you are ready to move quickly if the order comes. Preparation means taking the monitoring data seriously. The INGB publishes weekly bulletins for Campi Flegrei in Italian and in English. Reading them, not the sensationalized media coverage, but the actual bulletin, gives you the genuine assessment of the current state from the people who know the system most intimately. And preparation means holding the uncertainty honestly. The INGV does not know whether Campi Flegrei will erupt. Neither do the Italian Civil Protection Authorities. Neither does anyone else. The monitoring data tells us the system is in a state of elevated and escalating unrest. It does not tell us whether that unrest will resolve without an eruption, continue for years, or transition to a pre-eruptive phase. Living with that uncertainty, not dismissing it, not catastrophizing it, but holding it clearly and acting accordingly, is the specific psychological and practical challenge of living beside a caldera system in a state of unrest. The people of Naples have been living with this uncertainty for 2,000 years. They have developed a specific resilience and a specific relationship with the landscape that no other population has had to develop in quite the same way. But the scale of the risk and the scale of the potential event have never been larger than they are right now in 2026, with a monitoring system showing the highest sustained unrest values in the modern era and a population of 3 million people within the caldera's boundaries. The ground beneath Naples is moving. It has been moving continuously for 20 years, and the rate of movement is not decreasing. The monitoring continues. The INGV scientists review the data every morning. The civil protection authorities maintain the evacuation plans and the alert communication systems. The drills happen. The bulletins are published. The science is done. The volcano will do what the volcano will do. And the 3 million people who live above it are the reason that every centimeter of that ground movement matters. If this depth of analysis, the kind that takes the monitoring data seriously and explains the physics of what makes Campi Flegrei different from any other volcanic system on the planet, is useful to you, subscribe now and turn on notifications. The next video in this series covers the other major volcanic threat to a densely populated area that the mainstream media consistently underestimates. It involves a mountain you have almost certainly heard of, a population you did not know was in the danger zone, and a timeline for the next major event that is shorter than the consensus publicly acknowledges. In the comments below, after everything we have covered, I want to know one thing. If you lived in Naples, inside the caldera, with the monitoring data showing what it shows right now, what would you do? Stay, because the risk has been part of life here for 2,000 years, and the monitoring system provides the best available warning? Or leave, because the combination of uncertain warning time and 3 million simultaneous evacuees through inadequate infrastructure makes the risk management impossible? There is no objectively correct answer. That is the point. Tell me what you would choose and why. The most honest answer gets featured in the follow-up. If this is the kind of volcanic science you want more of, the real data, the real uncertainty, the real human stakes, subscribe and turn on notifications. The monitoring data updates every week, and so does this channel's analysis of it.